Good evening, everybody. My name is Dave Wheeler, and this is. Hi, what's up? So we're here to give you an announcement. Amazon is looking for cryptographers in our devices group. So, Amazon's doing amazing things in devices, cloud services, and automation. Our vision of ambient intelligence weaves AI together with services to increase our customer experiences. So sorry, marketing kind of had me say that, but this is where we need you. We need you to come to Amazon and join us. If you're interested in coming into industry, maybe you were influenced by Yehuda's talk and say, hey, maybe you need to come over and do some real work instead of living in the big O world, right? We're doing some really interesting things. We're working on post-quantum crypto for small devices, getting them to run on MCUs. We're working on improvements in classical protocols, getting them to run better, maybe run smaller. And we're making all kinds of things scalable and real world. We're even working on a satellite system, doing a worldwide key management system that's post-quantum secure. So if you're interested in any of those things, if you can code, we're interested in talking to you. So come find me, come find Luke, look up the job on LinkedIn, come talk to us. We're really interested in hearing what you have to bring to the table. Thank you.
Hello, crypto community. Hello, I'm Taekyung. Say my name. Yeah, I'm drunken, so yeah, I make it quick. So yeah. So I'm Taekyung and I'm representing Crypto Lab. This is a startup based on South Korea. So yeah. Oh. Yeah, we're basically making software libraries implementing CKKS homomorphic encryption, right? You know homomorphic encryption and CKKS. Yeah, CKKS stands for Chun, Kim, and Song. And Chun is actually founder and the CEO of my company. And it happens to my name. Last name is actually Kim, but I neither of these two guys, CKK, no. Because yes, there are so many Kims in South Korea. And not every Kims are related to, for example, Kim Jong-un or something. Oh yeah, basically, we're a company making software library implementing CKKS homomorphic encryption, right? CKKS is actually dealing with real numbers or approximate numbers, and yeah, approximate numbers. What is the important thing to consider when we do something approximate? Sorry. I think it's a precision and the speed, right? You don't agree? The bootstrapping. It is operation in the homomorphic encryption. It's a circuit to renew ciphertext to so that the users can do multiplications indefinitely. This is a very important operation. Why do you laugh? That's it. That's important. Actually, that is very important. Academically, the bootstrapping is very important. And our company provide the library that is a bootstrapping. The precision of the bootstrapping is very good. The major performance drawback is the bootstrapping in the most applications of the FHE. And our researchers actually found a new way to do bootstrapping. It's kind of meta BTS. It's improved the bit precision about 400%, 400%. Yeah, 400%. Very big compared to previous works. Yeah, we are very good. So Apply Crypto Lab. This is a company, very good company. Yeah. If you feel tired on the academic stuffs, then feel free to contact me to Apply Crypto Lab. So I can summarize meta BTS stuffs in one sentence. We can do bootstrap into, I don't know, BTS you can do two bootstraps in a row in a specific way to improve a high and achieve and high precision, Okay, I don't know, because I'm a team leader and our members do all the stuffs. Okay, and we are really fast. We adopt GPU accelerated. Okay. Okay, we are fast. We are really fast, and we release our library to the public in the September 1st, and you can download Docker images of our libraries. So, that's it. If you have any questions, contact me.
So hi everyone. I'm sorry I will disappoint after the bar was set so high with the previous talk, but I'm gonna give a serious talk about Scarf, which is a tweakable block cipher that we designed for a specific use case scenario, which is cache randomization. This is joint work with Tim Genesio, Gregor Leander, Jan Toma, Yosuke Todo, and Rei Ueno. So what cache randomization is, I'm not gonna go into details of that, but basically it's a mitigation, is a way to mitigate against side channel attacks that use cache contention, that make use of cache contention. And basically the idea is that you want to randomize the cache address, which is essentially composed by a tag and an index. I'm simplifying here, but basically, and the way you randomize it is that you take the tag part, which will be the tweak of your encryption, of your tweakable block cipher, and the index P will be the plain text of your tweakable block cipher. And already the interesting thing here is that the plain text, which is the index, is very small block length. So that's only 10 bits, which is very unusual. But what's most interesting and most unusual is perhaps the attacker model, which basically the attacker can only learn upon querying the encryption function, can only learn whether the ciphertext of two pairs of plain text and tweaks
collided or not, so it cannot learn anything about the value of the ciphertext itself. And basically, so far what has been done is have been proposed as encryption as way to randomize just block ciphers that are random reduced versions of known ciphers, and this is, I mean, with no security argument at all. And yeah, so what we try to do is, first of all, is understanding better the attacker model, and we try to reduce it to something more conventional. And so the idea is very simple. Basically, when you have a collision between two plaintext and tweaks, what this means is that actually you can see that one of the plaintext, in this case P2, is actually the decryption of the ciphertext, which means that actually what the attacker learns is that P1, so P2 is actually the ciphertext of P1 when you consider the composition of the encryption cipher composed with its inverse. So in other words, this means that when you have an R-round cipher E, as an attacker, you are attacking in a more conventional setting 2R round cipher E tilde, which again is the composition of your encryption cipher and its inverse under different tweaks, of course. And from this, you can see that not even if your encryption block cipher is secure, this does not imply that what the attacker see, which is E tilde, so the composition with the decryption, is actually secure. So what we did with Scarf is we tried to design a cipher that was secure in this model, and considering also the very short block length, we chose to use this MISTY++ structure, which has the advantage of having a non-invertible part, which eats a lot of key, which absorbs a lot of key, given the small block length, and also can update non-linearly the whole state in one round. And this allows us to obtain tweakable block cipher that has actually the latency of half prints. And so please look forward to it when we publish it next week. You're welcome to try, go and break it. Thanks.
Hurry up, hurry up, hurry up, hurry up, hurry up, hurry up.
All right. So I know I have a reputation of doing funny talks during rump sessions, but I did not have time this year to prepare a comedy talk. So instead, I have a proposal for how we can make reviewing more efficient. So let me show you a demo. Hold on, let me share in Zoom. Thank you.
That was barely audible in Zoom.
I'll fix it in post.
upper right, 2 diagonal arrows pointing away from each. There we go. No, the one below it.
All right. The dictator is beaten again on the prevalence of anamorphic cryptography. And while you guys are laughing and getting drunk, cryptography is under attack. So, all right. So in last Eurocrypt with Pino Persiano and Dong Yu Fan, we presented anamorphic encryption, how to keep privacy with respect to a dictator. And what is a dictator? So typical cryptography is developed under 2 conditions. The receiver keys are hidden for public key cryptography, and sender messages are chosen freely by the sender. However, we gave a scenario in which these 2 conditions are violated because there is a dictator which he knows the keys and it dictates the messages. And this is a little bit of a problem in cryptography, yes? But if the world were perfect, it wouldn't be. So, and governments are engaged in it, not even dictators, even democratic governments. And starting from the early 90s and the Clipper chip, the crypto wars are ongoing. And we have to tell the governments, is it a serious effort you are engaging in, or is this just exercise in futility? And therefore, we started this work. And in Eurocrypt, we show that even though the dictator owns your key, tells you which messages to send and verifies it, you can still beat the dictator and send messages that he cannot get. And we did it for 2 systems. One system based on CCA system based on the so-called Naur-Young paradigm. And under the hood, there is an anamorphic message. We call it anamorphic because it's a hidden one and you need a special way to view it. And you can do it while satisfying the dictator's requirements. You give the dictator the keys and you give it, and you follow the messages. And also we showed how to do it with LWE-based systems. And technically it's a combination of steganography, kleptography, subvertible encryption, and so on. But it feels good to beat a dictator, yes? This is the great dictator, Sir Charles Chaplin. And this is a movie from the 40s. If you don't know, it was a very predictive movie. Anyway, but natural open questions that we were asked by many, and we already asked ourselves, is how prevalent is this? Is just, are our things are examples or it's real? So the good news is that we realized that you can embed this anamorphic secrecy in new ways, in new crypto systems, in new places, new techniques, and under new models. So for example, you can do it with RSA, you can do it with Goldwasser-Mikali and TRU. You can change the model and get it with more system, put it in PAE, put it in signatures of sorts, piggyback encryption on other cryptographic protocols. So it's a very wide phenomenon using different techniques. So, you know, once again, the whole world laughs and the dictator is defeated. So that's the take. This is the take. So it is indeed, if somebody gives you very bad conditions to read your crypto, you can bypass it. And this is actually good news against all those that try to control crypto. So the conclusion is that anamorphic messages may not hide in plain sight, but they surely hide in cipher sight. Thank you.
Hello. I'll be presenting the work of our team in Emeritsec. Emeritsec is a group by Professor Huda Al-Khatimi in NYU and NYUAD. Our work is on machine learning framework for randomness verification and side channel attacks performance improvement. Okay, so the research objectives is that we are using the machine learning analysis to further evaluate our fabricated memristor in our labs. It's a fabricated memristor of copper, hafnium oxide, and highly doped silicon. We tested this. This is a previously published paper, but for further work, we tested it under machine learning analysis. And also we use the machine learning framework to improve the side channel attacks efficiencies through refining the selection of leakage model inputs to the training models, minimizing the imbalanced data sets for SPN and ARX. Hello? Yeah. And also for detecting design element changes required to improve certainties and attacks under study success rates, hence performance achieved. First, I'll start with the hybrid data sampling methods and ML-based side channel attacks. We are exploiting the leakage and combining it with the known principles of cryptographic algorithms for cryptanalytic purposes. Machine learning techniques have improved attack performance in profiling side channel attack. We investigate deep learning methods such as MLB and CNN. We also investigate samples of ML models to tackle the imbalance. Here you can see we have used different data sampling methods. We noticed that ensamples need to be greater than or equal to 10. Base ensamples inherently copes with imbalance in data. Addition of noise in data is in basic ensamples improved attack performance, and successful attacks needs only 200 traces compared to over 1,000 traces from a single optimized model. This is a significant attack performance improvement of 500%. As you can see here, the random under sample gives an acceptable attack performance, and we haven't used it. The basic ensample and noise ensamples perform better than all the data sampling techniques. Here we are presenting the work of the machine learning attacks or analysis done on the memristor-based buff to ensure the randomness and security of the memristor-based buff fabricated in our labs. As you can see, this figure, it's the set and reset cycles of the memristors. It's for every set and reset cycle, we have a different set and reset voltage. Thus, a random uncontrolled output. And this is the model of our fabricated memristor. Here the machine, here in this figure, you can see the machine learning general flow chart we've used. And this is for the logistic regression analysis that we've used. Here in the table, we have illustrated all the runtime complexities and the real-time execution. We finely tuned hyperparameters for logistic regression as VM, k-means, and k-means plus plus, GMM random forest, and XGBoost to evaluate our MR buff, the memristor-based buff, to ensure its randomness. And as you can see from this table of results, that the accuracy of the analysis was very low. And also for the ROC, it was low. Thus, ensuring the security of our MR buff. And thank you. If you have any questions, please send us on our emails. Thank you.
Yes, hello, thank you. Um, yes, there we go. Okay, so I'm afraid we're gonna have to have this talk again. Clearly, lots of you people weren't from Eurocrypt. While I appreciate your show of affection, please refrain from clapping. That's not what we do. If you want to show your affection, please. Thank you. Okay, so, and the second thing I wanted to say is just sorry to everybody I lied to. I didn't mean to lie. I really wasn't planning on holding like a second Limerick talk this time. But then something really embarrassing happened. And of course I had to tell you guys. So without further ado, it's just gonna be this one though, short and sweet. Yes. There once was this fella from Norway who lived with a self-locking doorway. The shower was good, but there he stood, half naked and stuck in the hallway. Thank you, that's all. Yes, break.
Okay, everybody, let's have one more round of applause and maybe some snaps for the speakers. And if you can do both at the same time, then you're very talented. Yeah, wow, we all look really stupid doing that. All right, everybody come back in 5 minutes. We have a 5-minute break.